Chapter Naples. Afcea is an international association, non-profit, with more than 5,000 membership, and is organized the international military panel inside the workshop of the IEEE. I would like to thank Professor Da Ponte, that is the chairman of this workshop. And I would like also to thank the Italian Air Force, the Italian Navy, and the Italian Army that gave the patronage at the workshop. As we are late, as in the conference, I would like to open the International Military Open with the first speaker, Engineer Guia Pastorini from Leonardo. She'll be present a lighter image, a new device that will be on board of.
Yeah. So good morning, everybody. My name is Guia Pastorini, and I'm working in the Leonardo Company in Florence site, Campi Bisenzio site. And today I'm presenting you the lighting imager, a state-of-the-art of the meteorological instrument. Here you have a mock-up. And I'm the project engineering manager of this instrument. Unfortunately, I'm alone. Carlo Simoncelli, the program manager, cannot participate. So I am alone today. So let's start from an overview of the lighting imager. Every time we check the weather forecast or we take a flight, we are using services that will be significantly improved when lighting imager will be flight. Let's see why. From almost 2 decades, the European Organization for the Exploitation of Meteorological Satellite, EUMETSAT, is providing meteorological data through the Meteosat second generation, launched in 2002 until 2015. As the Meteosat second generation is approaching to the end of its lifetime, EUMETSAT, with the support of ESA, developed in 2010, launched in 2010 the development of the third generation. Its operational lifetime will be covered by 4 imager satellites and 2 sounder satellites. Meteosat third generation is, of course, an evolution of its predecessor, making a step ahead in terms of performances and technological challenging. One of these is the implementation of a lighting imager, the first in Europe. But what is it exactly, a lighting imager? It is basically a big camera with a sort of artificial intelligence able to perform from geostationary orbit continuous detection of lighting with a very high spatial resolution, about 5 kilometers, covering the 84% of Earth disk, and with a low probability of false alarm. All of that in different type of scenario, because we are looking at Earth during night, during day, we are looking oceans, we are looking lands. So all these characteristics have to be maintained in different type of scenario. Why it's important to have a lighting imager? Of course, for nowcasting and short-range forecasting of severe weather and convective events, to study and monitor the physical and chemical process in the atmosphere, as for example, the nitrogen oxide production, to monitor the long lighting and the atmosphere characteristics, for air traffic safety, and also for the validation of a satellite-based weather forecast algorithm. Lighting imager is the first lightning hunter in Europe, and is the first one worldwide with such performances. And it will be seen in the last slide, we will perform a comparison with respect to the measured competitor. This is a picture of the industrial team, which is very spread. So Thales Alenia Space France is the MTG prime contractor, while Leonardo is the LI prime contractor, both for instrument and for processor, for mission, because we are also responsible of the level 0 and level 1 algorithm process. The presence of Italy is not only limited to Leonardo Company, but also Thales Alenia Space Italy is involved performing the software, but also the SBC. So in this instrument, we have the first power PC flying. This has been a very technological challenge. In addition to the Italy, we have also Belgium for what concerns the detector, Ostrich for what concerns the MLI, and also the Holland for the ground processor algorithm. This is only a limited picture because, as you can imagine, there is a big list of several other partners and suppliers in Italy and abroad. The contract value is about 80 million euros, mega euros. And the duration started from September 2012 until December 2024. Here you have a sketch of the timeline of the instrument. As you can see, the development phase takes a long time, more than expected. Starting from 2012, we have been able to froze the design only in 2019, because we faced two very big, important technological challenges. Also, the integration and the test phase of the first model was longer than expected. The integration of the first model started in 2020, and we have been able to deliver the instrument to the satellite in March of this year. So this diamond have to be put here, okay? Currently, the instrument is integrated on the satellite for the test at satellite level. The overall mission foreseen also the presence of 3 recurrent models, which are under integration in Leonardo Company. The first one will be launched some years after the first one, and the third and the fourth one will be put in storage for an overall mission of 25 years. So let's see more in details, which is the lighting imager. This is a first overview of the instrument. So as you can see, the instrument is composed by 2 main subsystems. The optical head, for which we have a dummy here in front of us. This mock-up is a vintage lighting imager because the design has been improved and changed with respect to what is shown in the mock-up. In any case, we have 4 optical channels. These are the baffle to remove the solar spectrum. And this optical head has a total mass of about 100 kilograms. Here we have the main electronic, the one implementing the power PC flying, which is 12 kilograms, and it is installed in a different part of the satellite. The 2 subsystems are separated by more than 2 meters of spacewise cable. In order to understand the instrument peculiarity, we have, first of all, focus our attention on what we have to detect. So lighting imager is able to detect intra-cloud and cloud-to-ground lighting pulses with very stringent characteristics. A lighting pulse is a signal very fast, taking into account that the minimum duration, the minimum pulse duration that we are asked to detect is only 0.6 milliseconds. That means a signal which is 1,000 faster with respect to the high blink. Just to give you an idea. The signal is also variable in dimension. The lighting pulse can have a variable dimension, and we are asked to detect the minimum dimension that we are asked to detect is 10 kilometers of diameter. But seen from geostationary orbit, that means that the moon in the sky appears 33 times greater with respect to the dimension that we are asked to detect. The signal is also characterized by a very spectral range because the lighting pulse, the triplet, the oxygen triplet, is centered in the 777.58 nanometers with a bandwidth range of just about 0.17 nanometer. That means that the spectrum covered by a light pulse is only 6,000ths of the spectra that our eyes can detect. Finally, the intensity of the signal, because some lighting can be very bright, but we are asked to detect also weak lightning pulse, but we have to consider that the intensity of the lighting pulse is always overimposed on a dynamic range Earth background. because the characteristic of the instrument, the performance of the instrument have to be maintained when we look at the desert, so a flat background. When we are looking at the ice, the north part of the Europe, when we are looking the ocean with the sun reflecting into, and we are looking the urban area, maybe during the night. So all of that makes the receipt of the lighting imager very complicated. So which are the main ingredients? What has been the design phase main focus? First of all, we need good eyes. That means an optical design to detect weak, fast, few, and small optical pulses in a very narrow wavelength range. We need also a good brain, because we need a detection chain concept able to identify the observed Earth scenario, understand which kind of scenario is, and implement a real-time evaluation suitable for the specific observed scene as an artificial intelligence. We need the flexibility because we need to work in different scenarios without bottleneck, also in the worst flight, not nominal condition, to maintain a constant flux of data through satellite. This has been a very stringent requirement. We will see later what does it mean. Of course, we need a good body, so a thermomechanical structure to grant a lifetime of 8.5 years in geostationary orbit, and high reliability, because being not possible to intervene during the operational life, we need complex simulation model to predict the LI behavior, to understand in advance which could be the LI behavior in flight. And finally, all of that with very stringent constraints given by the satellite, not only related to the weight or the dimension, but also on the generated noise, because of course we have not to disturb the other part of the satellite. How we have obtained it? We have realized an optomechanical athermalized design. So as you can see, we have 4 optical identical channels tilted to grant the 84% of Earth disk coverage. And each optical channel is characterized by a telescope realized by 5 lenses, one of it is a spherical, in a quite rapid optical design because we have an F number of 1.73. And this is combined with a passive thermalization concept because the performance of the telescope have to be maintained between 15 and 50 degrees during the whole operative life with an energy, an squared energy greater than 90% end of life. The spectral resolution, so the spectral identification of the light pulse is realized thanks to a narrowband filter with a bandwidth of 1.6 nanometer in all operative conditions. That means regardless to the angle of incident, to the aging, to the temperature, centered on the oxygen triplet. This has been a very important technological challenge. This filter has been realized by Iridium, a Canadian company. And this filter is working coupled with a sun rejection window, so a filter to remove the spectral, the sun spectral range installed on the baffle. So in each baffle, we have also a solar rejection window. We have seen that we need also a powerful and high configurable detection chain, free of bottleneck, to cope with the worst case not nominal in flight scenario. So an important role in this is played by the front-end electronics, this C-shape surrounding the telescope. The front-end electronic contains, each front-end electronic contains 4 ASIC and 1 FPGA, and both of them are part of the heavy onboard mechanism process, which will be described in the next slide. Because we need also to have an autonomous data regulation to manage a variable flux of fault transient and true transient, providing constant data rate versus platform. The detection is realized by an high quantum efficiency backside illuminated CMOS technology, realized in Belgium, with an high throughput. Consider that each detector is providing 12 gigabytes per second of data through 60 LVDS line. What does it mean that? It means that each second, 48 gigabytes per second of data are provided by detector, but we are asked to produce and to process, to send to the platform only 30 megabits per second, constant in each condition. That means we have to implement a heavy onboard post-processing, and one step of this onboard post-processing is realized by the ASIC, thanks to a real-time pixel processor. One is inside the FPGA for the single detection filter, and other one is inside the main electronic for a micro vibration filter and for an autonomous data regulation system. For what concerns the thermomechanical structure, the structure is realized in composite material, interfaced with the satellite by titanium bipod mounting in a quasi-static configuration to grant the thermoelastic compatibility with the satellite and also to the low mass stiffness strength ratio. The thermal design has to cope not only with the dissipation of the 4 FPA and front end, but also with the orbital heat fluxes directly incoming in each baffle. So what we have realized is a radiator faced to the cold plate, to the cold space, sorry, heat pipe system, and this has been realized in Spain by a company in Spain. An MLI blanket, so this dark Kapton covering the whole instrument, and thanks to an operative and survival thermal control system. Last but not least, the team working. So here I am alone, but please consider that I'm talking on behalf of more than 30 engineers, very specialists, and without them, this technological challenge would have not been achieved. These are some pictures taken during the test of the lighting imager. Here you can see the optical head during the acoustic test performed in satellite Rome, in the, TASAI Rome premises. Here we have the optical head during the sine vibration. And these two pictures are taken directly in Campi Bisenzio premises. Here you have the whole system, LOH plus LME, and these are the cable. And they are ready for thermal vacuum test inside the same thermal vacuum chamber. Here, this is the configuration used for the calibration of the instrument. The optical head has been mounted in horizontal position thanks to an hexapod, which is not shown here because it's covered by this service MLI. And this hexapod is moving when the instrument is inside the thermal vacuum chamber, the instrument in order to face each optical channel in front of the optical window, because outside that there is an optical pulse used to calibrate, to perform the calibration of the instrument. Currently, the instrument is mounted on satellite level, so it's performing the functional test, and the launch is foreseen for November. Unfortunately, the activities at satellite have been shortened due to the fact that the planning was to fly to Kourou using the Antonov, but unfortunately we need to change our approach, and so we will go by both. So this has shortened the activities at satellite level to maintain the launch data. The vector will be the Ariane 5. Finally, the last slide, you can see some pictures taken during the integration. So here you have the telescope. Here you have the radiator. So the structure for the radiator, the upper part is devoted to the front-end electronics. The lower part is devoted to the detector. The heat pipe shown here are the system to drive the heat from the electronics to the radiator. This image is taken from bottom, so the instrument is mounted on a ground support equipment used to rotate it. So you can see here the interface of the bipod, this one, and this one. These C-shape are the front-end electronics, each one for each detector, for each channel. And these red square are the cover of the reference mirror, which are used to characterize the position of each optical channel during the test. Of course, this cover will be removed before, have been removed before the final integration phase. And here, this is a picture of the board before the integration, just to give you an idea of some step of our integration phase. Okay, yes. Here to show you why we see that the instrument is the first in Europe with these characteristics. Because if we compare lighting imager with a measured competitor, we see that we have a very higher spatial resolution, 4.5 kilometers instead of 8. But in particular, it's important to check the minimum detectable lightning pulse energy for instead of 10 microjoule per steradian per square meter. And the most important one is the fact that our instrument is able to detect a single pulse, single events, and the average detection probability is greater than 70% for the minimum detectable pulse energy, the minimum dimension, and the minimum duration. Our competitor is not able to check, to detect single pulses, but only flashes, so group of pulses. Thanks for your attention.
Thank you, Guia. Your presentation has been very interesting. Can you give us more details related to the launch of the light imager? Where will be the remote control station, or
okay,
which are the next steps for
okay, the next step are the completion of the test at satellite. So we are performing the functional test. Then we will be the electrocompatibility EMC test, the electrocompatibility test, and then it will be sent by both to French Guiana for the launch through the Ariane 5. And the ground processor will be found in EUMETSAT, so in Holland, and also in Darmstadt, where there is the ground control. And that's all. So in Leonardo Campi, in Leonardo premises, we are proceeding with the integration of the 3 recurrent models. So we are proceeding with the integration. So we have also performed some important step of the integration of the FM2 and the FM3, for example. The optical bench plus the bipod have been already mounted and characterized.
Thank you. Are there any questions to Ms. Guia? Yes, please, Engineer Fugget. Thank you very much. I hope that the Navy cadets that are together with us today would be a good chance for them to know this device. And I want to give you a good luck for the launch and for all we cross the fingers.
Exactly, that is important. Okay.
Thank you very much.
Thank you very much.
Thank you very much, Engineer Fugget and Guia. Before the presentation of the next speaker, I would like to thank Professor Tellini that he's hosting us the military panel today, and I would like to give a warm welcome to the first astronaut, Franco Malerba. Thank you very much, Frank. Then the next speaker is the 46th Brigade Commander, Brigadier General Alessandro Di Lorenzo. I met him when he was a young lieutenant, flew F-104. I'm very glad today to meet you again as a Brigade Commander. Please, the floor is for you.
Hi, good morning to all. We come from the space, we go down to here, to Pisa, and fly inside the space, not aerospace. So I'm the base commander of the 46th Air Brigade. Is a Air Force unity that is here on Pisa. Probably whoever is Pisa all surrounded know about the 46th Brigade. I'd like to give a quick glance about what we do inside Pisa and with our fleet. We go through a quick introduction and what we have on the fleet, some support, especially with the COVID, and then some guideline for future. This is pretty much where we are. We are in Pisa. This is the Air Brigade. It is probably it is the only brigade in Italy where there is a commander, there is a one-star general, and that has airplane under their command. We are in San Giusto airfield. There was a former training field in the 1920s, so one of the first airfield in Italy. And around the 40 was converted into a military field. One thing that I like to remember, there is a military field that is open to civilian traffic, so there is all the problem with the military plane and all the problem to be solved with the civilian plane. Under my command, there is Pisa, there is also Luni Sarzana, there is the airfield where coexist the Navy and the Air Force, and there is some other meteo telepost around Italy that depends logistic from the brigade. A little bit of background, as I say, started in 1940. It was a fighter bomber squadron with the SM-79. It was the first unit to be converted in the anti-ship war. So one very predecessor of airplane, the SM-79 that can launch the torpedoes in air. After World War II, it was converted into a transport, tactical transport unit, because since then there was the understanding that there was the need for air transport, not only in the military side, but also in the civilian side. In fact, one of the first planes that was used by the brigade was the C-119. The flying boxcar was a US-made airplane, and probably the first real transport plane. Two engine with the piston engine with pretty much 3,400 horsepower, probably the biggest piston engine ever built and put on a plane. Start flying in 1954 with this plane all around the world. So for whoever is acquainted with the flying, and meteorological conditions were very important to know when you fly with a plane that does not have a radar, where the radar does not can climb above clouds because it's not pressurized, so the maximum altitude it can fly was 10,000 to 13,000 feet. And we flew all over the world. A lot of missions were under the United Nations flag. One of the important was in Congo in 1961 when there was a huge tragedy for the Italian Air Force where 13 crew members were killed by military in the zone. So not in plane, but outside the plane. Changed the fleet in 1972 with the C-130H first, then 1977 with the G222, an all Italian-made airplane, very nice design. And both planes were changed through a midlife update in the year 2000, C-130 in 2000 with a new avionic, all electronic inside the new engine. And in a joint venture between Leonardo and Lockheed Martin, they put the same system, pretty much the same system on the C-27J, coming from the G222, changed the engine, all the avionics. Our fleet, today's fleet is 20 C-130J in a different version. There is a long version and a short version, and can be configured for different mission. One particular is air-to-air refueling. It is one of the few planes that can refuel helicopters, so can refuel fighters and helicopters. Search and rescue mission, and logistic mission. The other plane is the C-27-12 body made for the Italian Air Force. There are 11 are here in Pisa. One is in Pratica di Mare for testing purpose in several versions. There is a logistic transport version, electronic attack version, special ops version. What we do with this plane, we said that logistic transport, we can load from the axial door, so can load large body or long body system, probably the satellite if they need to transport the payload, we probably can do with the C-130. C-27 a little bit less capable for transport, C-130J a little bit more capable. The same plane are used, there is one plane that is always 24-hour in standby for 365 days a year for eventually medevac or sanitary purpose. We can load an ambulance inside the plane. Air-to-air refueling, we talk about fixed wing and rotary wings. Can land and take off out of all kind of surface, so prepared and unprepared surface, and also the pack in Antarctica. Airdrops, personnel, and load of all things, and with the C-27J, we can do also electronic warfare attack. The vision for the brigades are strong, cohesive, and motivated brigades, ever ready to meet the country's needs. I brought here some of the capabilities that are very peculiar to this wing, Italian wing, that you cannot find easily around the world, so they're very used. One is the search and rescue. The needs was to escort a fighter plane that would fly across the pond, across the ocean, and in case of ejection, be ready to give immediate support to the crew. So can you imagine just to bail out in the middle of the ocean within 3,000 miles away from the coast and just have the small ship that goes with the ejection seat. So the needs was to bring immediate support. So find the crew and launch very precise a system that can allow the crew to survive until someone can rescue. And so this is a system that we totally developed inside the Italian Test Center, and is still in the year 2000 is still used. There is precision airdrops. In case you need to airdrops cargo up to 1,100 pounds of payloads, we have a system that is controlled through GPS. You can input the desired impact point and release from a plane, and is very precise. You can bring this load up to 5 meters from the desired impact point. And we just test them also and exercise them in an exercise in Portugal a couple of weeks ago. Another system is for special ops, is to be able to drop. We can drop almost everything that can fit in the plane outside. And one nice thing is an inflatable boat that is very, very long. It's a 7 meter and 33, and we can launch in wherever there is needed all around the world. So we can load here in Pisa and fly wherever is needed and launch almost in very rapid, with a very rapid reaction time. As I say, we can land in gravel, we can land in the desert, but we also land in Antarctica, in the Antarctic operation, for Antarctic operation in the South Pole. Taking off for New Zealand, it's about 7 hour of fly, and then land on a pack on an unprepared surface on the ice. There's not a lot of plane that can do that, either for weight, either for kind of reverse thrust to break the plane, and also be able to take off and resist to very low temperature. There was the last mission that we had in this field was in last October and November, and I had planes that were flying in a minus 50 degrees Celsius, and planes that were in in Africa and in Middle East, flying are more than 50 degrees. So we had 100 degrees of exchange temperature. Probably everybody know about the Kabul evacuation that was made almost a year ago, last August, and the 46th Brigade was deeply involved with the plane. Suddenly, very rapid reaction time, we had to take off out of PISA, redeploy in Kuwait, and be able to fly from Kuwait to Afghanistan and come back with a lot of refugees. We were able in about 20 days to bring back 5,000 refugees, and with 5 planes. You compare to the US that probably brought 23,000 people with 135 planes. So this is pretty much the comparison of what we were able to do in that mission. It was a very difficult mission, about 22 hours of duty for the crew, very stressful, but at the end we managed to bring back as much as refugees and all the refugees that the Italian government was the objective to bring back. Another support that took us very busy in the last 2 years was the support to all other government agency, Italian government agency on the COVID-19 fight. Different kind of mission was one. The first one was for transport of protection device. That was in March, April 2020. The only plane that were flying in Italy was the airplane from the 46th Brigade. No civilian plane, no other military plane that were flying. It was pretty nice because you can go point to point without any traffic. Another capability that we have is biocontainment transport. We can transport heal people of COVID or other contagious disease safely for the crew. So the sick people will be put in this kind of baggage with support crew and fly all over the world with no risk for the crew. And we really use a lot during COVID fight. Another one was for vaccine transportation. I remember I did one of the first flights on the 26th of December of 2020 to bring vaccine from Rome all over to Italy. This is pretty much a quick glance about the biocontainment. We have 2 different systems. One is a bigger one that you can, the sick people can be a little bit more comfortable inside. The other one is a smaller one that can be also carried with the helicopters. And this is the flight activity with the vaccine. We still do, especially for island, when we need to transport the vaccine to island. A lot of people that we need to transport were people that were working in a theater, in the operational theater, that need to be brought back in Italy, and we did a lot of all our armed forces. Another center of excellence I'd like to talk about the 46th Brigade is the training center. We have a very advanced training center for both C-130 and C-27J. We have a Class A simulator. Class A simulator for who want to become pilots are simulators that are perfectly equivalent to the plane. You can fly on the sim and then be able to fly as a co-pilot in the civilian world. A lot of commercial airliners train people with this kind of simulator. They do the sim and then they go and directly fly with no flying activity on the plane directly in the fleet. We have 2 sim. We train not only Italian pilots, we train pilots, actually crew, because it's pilots, loadmaster, also maintainers from all over the world. C-130J, we go from Middle East to Europe, even French and Germany comes and train with us. C-27J, this is the only Class A sim of the C-27J, and all the customers of C-27J come and train in Italy for us. we have really a good feedback from all the people that we train. And also nice because it's more or less we standardize all the crews to fly on C-130 and C-27J. So all of them, all the user at the end comes out standardize how to operate these two assets. This is pretty much it. I'll leave some time for questions. Whoever has got a burning questions, feel free to ask.
Thank you, General Di Lorenzo. I have just a simple question. How many flight hours fly your pilot at your brigade every year?
Yes, we have crews. Our crews, the operational crews, they go at minimum 240 flying hours per year, up to have someone that also reach 400. So it's all you can eat. There's no limit. There's no limit on whatever you like to fly. A lot of them, a lot of flight hours are made in the theater. So we have constantly deployed one airplane in the Middle East, and the one is in Africa and Niger. So a lot of flying hours are made, in the theater. A lot of other hours are made here in-house. Pretty much the needs for logistic transport is well behind our capability of flying plane. So the crew are whoever likes to fly, this is the place to come and fly.
Great, congratulations.
Thank you.
Thank you. I think that we are on time, then we can continue with the next speakers, two speakers from the flight test wing, two young engineers. They are born in 1993, they are already involved in an Air Force aerospace program, and they will talk regarding a program related with Virgin Galactic.
Good afternoon, everyone. I'm First Lieutenant Marco Rigamonti. I'm working at the Italian Air Force Flight Test Wing. And I'm here today with my colleague, First Lieutenant Giorgio Vastarella. He's working also at the Flight Test Wing in Pratica di Mare. We are presenting a flight test instrumentation for motion sickness research in the suborbital environment. This experiment has been mostly done thanks to the help of Major Jacopo Covioli, who we want to thank because he was the main responsible of this activity and unfortunately is not present for duties today. At the agenda, we will have a brief introduction, just 2 slides on what suborbital flights are and which are what they represent for the future of space research and space activities. And we will understand why it's important to know human physiology and how humans react in different G environments. And then Giorgio will present the experiment and we will have the conclusion at the end. So going to the introduction, so suborbital flight is a new frontier. I'm sure that most of us knows what a suborbital flight is. Basically, today we have 2 current valuable options, which are the well-known Virgin Galactic Spaceship 2 and the Blue Shepard from, which are 2 different systems. Virgin Galactic is an air launch system. So basically, we have an aircraft carrier that is bringing the spaceship below the wing, and it's going up to 50,000 feet, and then they launch, they release the ship, and they launch the ship that goes up till 80 kilometers. While on the other side, we have Blue Shepard, which is like a basically it's a missile, a rocket with a capsule on top, and they can reach 100 and more kilometers at the top of the parabola. Basically, the flight path is a sort of parabola, and the top of the parabola we have the microgravity phase. Why suborbital flights are very important? Well, we can see on the right image, I put like some traditional platforms we use to do experiments or to in different variable G environments. So we have on the left a centrifuge, sounding rockets, parabolic flights. We have drop towers and the space station, of course. So they have different length of time for preparation of the experiments. Some of them can bring astronauts or researchers as parabolic flights or the ISS. Parabolic suborbital flights are similar to parabolic flights, and at the same time they are similar to sounding rockets because they take the combination of the advantages. From one side, we have more time of microgravity, so we can bring from the 20 seconds of parabolic flights, we can reach in suborbital flights around 3.5 minutes of microgravity, and at the same time they can bring researchers on board. This is very important because from one side, it's possible to enable the collection of more data on people, so on a wide plateau of test subjects, and at the same time, it's possible to open space to public. So that's the reason why we hear about space tourism. For this reason, it's important to understand human physiology, not only in microgravity itself, but also in all the flight path, especially for the Virgin Galactic. We are discussing mainly about Virgin Galactic because the Air Force has reached an agreement with Virgin Galactic to do the first Air Force suborbital flight with the Spaceship 1, Spaceship 2. So this type of flight, we can see there on the right, and we'll see later better in depth. It's characterized by rapid changes in G environments. So from the release, we have like a pull-up maneuver, so the people can experience 4G environment, and they have a 0G environment, and then when they come back, they can reach 3.5 Gs. So it's important to understand how the body reacts, and especially considering that we don't have any more well-trained astronauts, but if we have space tourism and we have researchers, we will have like basically normal people, standard people that are going in space or at the edge of space. And this is very important to understand how normal people react to microgravity and to different variable G environment. So I put here some interesting facts. For example, there is sensory motor disruption, cognitive performance deficiencies, and of course there is motion sickness. And our experiment is focused on this motion sickness. So motion sickness is a key factor to evaluate the passenger's comfort, especially in this case for Virgin Galactic. So vibrations, experience, and G variations during the different launch and flight path. It's important to avoid that people on board are feeling sick. So it's important to understand if it's possible to understand. Sorry for double joke. If it's impossible to understand that people, considering the variation of vibration, can experience vomiting incidents or can experience motion sickness during all the phases. Go to the experiment, and I leave the stage to my colleague Giorgio, which will explain the experiment in depth.
Thank you, Marco, for your introduction. So, good morning, audience. I'm First Lieutenant Giorgio Vastarella, Reparto Sperimentale di Volo from Pratica di Mare, Flight Test Center. I will discuss the experiment that our flight test branch have carried out and that have been integrated on the Virgin Galactic Spaceship 2, tested, verified, and certified from Virgin Galactic. So I don't want to bother you with any kind of math, but it's just to make a sort of context. What we have done, so the requirement against which we have installed integrated flight test instrumentation on board the aircraft derived from a medical and physiological approach, an empirical one, aiming at quantifying the incidence of the motion sickness in terms of percentage on people exposed to such kind of G variation, and in general exposure to this kind of let's say fields. So for those of you who have experienced like more than 1G exposure in an aircraft, talking about more than 2, can perfectly understand that what people feels is quite different than from what normally people feels on a normal commercial aircraft. And that's the reason why on, for example, jet aircraft, people wear, pilots or crew in general, wear anti-G suit, sorry. For this kind of flights, so commercial flights, people are not expected to wear such kind of equipment, piece of equipment. And so as a commercial flights are keeping up more and more, there's a great interest in understand how people, normal people, without wearing any kind of G Suite or equipment, as I was mentioning before, how they react to this kind of solicitations. This formula here is what from an empirical study have been produced to quantify the incidence of the vomiting on people, so motion sickness resulting in vomit. And yeah, as I was saying before, we won't go inside the formula, but it's basically the core of this formula is the acceleration to which the, as I say, personnel is exposed. And it depends on the time, the time duration to which the personnel is exposed to this kind of solicitation and the acceleration they feels. Starting from the mission requirements, as Marco introduced before, the Italian Air Force, basically in conjunction with other government institutions such as the CNR, for example, basically bought a flight from Virgin Galactic to make some sort of experiments both in the climb and descent phase and in the almost zero gravity phase, so the microgravity phase. We will focus on the climb and descent, so those phases where no microgravity is experienced. So before the passenger basically unlatch, when they are still latched on their seats. The phases of flight are here exposed in the picture. So we have a mated takeoff, mated because the Virgin Galactic spaceship is basically brought to altitude to more or less 45,000 feet from a mothership, which is White Knight 2. And then from that point on, the separation occurs, so which is the second phase. Separation occurs, so the rocket motors light and the spaceship climb up to 300,000 feet. That's a phase where a 5G pull-up is done, and basically the spaceship reaches the apogee. Personnel on board feels that experience the 3.5 more or less minutes of microgravity, and then the spaceship comes back. So there's a re-entry and glide phase. What is the payload that we have designed, our flight test instrumentation branch have designed? It consists of two main parts, let's say. One is the brain, and the other one is the measurement tool, the transducer. Starting from the latter, basically we have installed 3 triaxial MEMS accelerometers, so micro electronic measurement system, with no losses in the 0.1, 0.5 hertz band, which is the one that is predicted that people will experience compared with the studies that have been done from a model, from a simulation and modeling point of view. And those accelerometers have been mounted on the seats, on one seat in particular, for a total of 9 measurement channels, which are 3 axes, so X, Y, and Z, for 3 accelerometers. And data collected by these transducers, acceleration transducer, are collected and then elaborated by the brain, which is a data acquisition unit. In particular, the one that we have used is called the ACRA-CAM 500. And so these signals are acquired by an analogic differential-ended measurement module, elaborated and then stored basically in the device. What is important here, because everything that I have said so far is what we normally do for any kind of same measurements that we do on normal aircraft. The difference here is that the payload had to be installed on something that goes more or less in the space, a little bit lower than space. And this have been a very difficult thing to cope with in terms of certification of the payload. In fact, the data acquisition unit had to be enclosed in an aluminum case, which have been produced by the flight test center itself. So it's a whole, let's say, house-made payload from the accelerometers to the data acquisition unit to the case. As I was anticipating, the payload had to go through a very difficult process of verification, and as it had to comply with a great number of Virgin Galactic imposed requirements, against which a great number of tests, both from a simulating point of view and mechanical, physical point of view, have been carried out by our personnel, especially from by Major Jacopo Covioli, who unfortunately is not here today. But basically, in order to certify the structural resistance, electrical and electromagnetical compatibility of the payload and thermal compatibility of the payload. After which is the one thing that I am about to say is a very great goal that we are very proud of. We have been certified by Virgin Galactic, so the payload has been certified by Virgin Galactic. So in terms of methodology, what we practically are going to do is to install these accelerometers and the payload in the spaceship, collect measurements of accelerations, of vibrations basically, of the seat during the climb phase and during the re-entry. Obviously, the seat dynamics will change due to the fact that the passenger is seated on the seat. In fact, let's say the state of the art of this kind of measurement would have been to install, but it's not possible, unfortunately, this accelerometers on the body itself, because it's the one thing where measurements should be collected. Unfortunately, due to Virgin Galactic's requirement and limits, it has not been possible, and it was not possible to install the mannequin as well. So we have to rely upon the seat. And so we have defined, after some basically modeling and simulation tests, 3 suitable positions for the optimal position for the accelerometers, which were basically presented in the picture before. And there we have placed the accelerometers. Data will be collected, so as I was saying, with the passengers seated. This is basically what I have to do, pretty much what I have to do. And I want to stress just one more thing that Marco was anticipating. So why we have done this, why we are doing this. For instance, we have actually installed this payload in the spaceship. We have gone to New Mexico and we have done that. Unfortunately, the flight have not taken place due to basically other things that did not depend on. Do not depend by anyone, basically, if not the FAA, who declared Virgin Galactic not ready for flights. So, but we are expecting the flight to take place. We hope as soon as possible. The one thing that I want to stress, and then I will close my speech, is that we cannot do this kind of things on normal aircraft. This is the reason why we have done this thing, because maybe you can think, okay, you just have to install this kind of instrumentation. Why don't you do it on a normal aircraft? Reason is that on normal aircraft, like a fighter, has a complete different seat with respect to the one that Virgin Galactic uses. In general, that kind of seat is very different to a commercial one, which is designed because it is designed to be ejected for a lot of other requirements. So that's the reason why we definitely had to go and install those kind of things on the spaceship itself. Thank you.
Thank you, Vastarella and Rigamonti. Very interesting, your presentation. Are there any questions from the floor? Then it's 1 o'clock, lunchtime. Then, please, Professor De Ponte.
Thank you.
A curiosity about thank you for the presentation. The data acquisition system that you put close to the seat, what are the characteristics of the analog to digital converter? There are some special performance for this type of application. Is it a commercial product? Thank you.
Mr. Professor, this is let's say commercial product, but it's a very peculiar commercial product because it's a state of the art of the data acquisition unit that are used for flight tests all over the world. So Lockheed Martin, Boeing, Leonardo, we use this kind of instrumentations. we can say that Curtis Wright, who is the producer of this kind of things, and Zodiac, which is the competitor, the French competitor, have the lead in projecting and in designing and producing this instrumentation. So they comply with everything that's related to the airworthiness. So they are fit to fly, and they can reach very high performance in terms of sampling. It's a sigma to the sigma delta ratio converter inside at the very core of this kind of module. But this is just one module of the data acquisition unit, which is the Acra CAM 500. We can install many kind of modules depending on what kind of acquisition we have to do. In this particular application, we use an analog module, but we have bus module for aircraft bus acquisition, digital module, RF signal acquisition module, PPS. There's a ton of different modules.
Okay, thank you. We'll be back here at 2 o'clock. The next speaker will be Colonel Johan Galland from the Royal Military Brussels, Belgium. Thank you very much.